So the next topic in regression is the use of interactions and the concept of interactions. So linear regression makes a very strong assumption that the dependence of y on each one of the predictor variables is just a linear function with some coefficient in front. So we can expand this idea to more complicated terms. So for instance, instead of having beta 1 x1 plus beta 2 x2, we can have those two terms plus beta 3 x1 times x2. So this multiplication is what is called the interaction term. And this the addition of this term allows going from hyperplanes, that are the ones that can be defined with just the plane variables without any interaction, to more complicated surfaces. Actually, we can think of this x1 times x2 as part of the Taylor expansion of the function. So in the Taylor expansion, we would have all these multiplicative terms of mixed variables. Okay, so now we can reinterpret this term beta 3 x1 times x2. We can factor out the term x1 and also taking into account this beta 1 x1 to write it in this way. So what we have is that the slope or the dependence of y on x1 depends on x2. So the addition of these multiplicative terms makes that we have more freedom to express what is the slope of y on x1, but now depending on x2. And we have done the analysis based on x2 or the slope of x1, but we could have a similar analysis with x2. So now the effective slope is now a function of x2. So when we feed this interaction model, these interaction terms, it applies something that is called the hierarchical principle. That is that if we include an interaction in a model, we should also include the main effects, even if the p-values associated to its coefficients are not significant. And the reason is that if x1 times x2 is related to the response, then whether the coefficients of x1 or x2 are exactly zero is really of little interest. And also x1 x2 times x2 is correlated to x1 and x2, and so leaving them out tends to alter the meaning of the interaction. So let's have an example. So we construct this function. So it is beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2 plus some noise. The standard deviation of the noise is 1.5, and x1 and x2 are uniformly distributed in the segment 0, 5, and we will have 500 samples. So we have here x1, x2, so we see they have a uniform distribution between 0 and 5, and they are uncorrelated to each other. And then when we construct y, this is the dependence of y onto x1 and x2. So we see that this is a correlation matrix. x1 and x2 are uncorrelated, and y is correlated to x1 and x2 as expected. Okay, so this is the plot of the data of the observations. So now we can make a fitting of a linear model without considering the interaction. So we see all the coefficients are significant. The p-value of the model is pretty good, meaning that we have explained something of the model. We have explained almost 90% of the variability, And since we know that there is an interaction and we generated the data, we know that these coefficients are not the correct ones. And when we do the residual analysis, we realize that there are patterns in the residuals. So the model has been misspecified. So the family of models that we are fitting is not the one that has generated the data. So the data is not generated by this simple model. So let's try to do a more complicated model. So now we include the interaction, and again, all the coefficients are significant. Now all the estimates of the coefficients are correct. Just a reminder, this was 10, 2, 3, and 5. So we have now pretty good estimates of those true parameters. The R-squared is extremely good. The p-value of the model is extremely good. And this notation is the one of MATLAB to indicate what is the interaction. So this is the coefficient, this is beta 3, the term that goes, the coefficient that goes in front of the term x1 times x2. Okay, so now the residual analysis doesn't show any particular pattern, so we are pretty happy with this model. There is this concept of interaction also applies when we have quantitative and qualitative variables, so continuous variables and categorical variables. So if we don't consider interactions, so let's say that x2 is a categorical variable. So if we don't consider interactions, when x2 takes the 0 value, y is beta 0 plus beta 1 x1. So this is this blue line here. When x2 is 1, then the intercept is beta 0 plus beta 2 and then plus beta 1 x1. So that means that we are shifting up or down our regression line. So when we have x2 equals 0, we have one line. When we have x2 equal 1, we have another line. If we add the interaction between x1 and x2, then doing the same kind of analysis that we did before, where we grouped, we factor out x1, so the intercept now would become beta 1 plus beta 3 x2. So that depends. So depending on whether we have x2 equals 0, we will have a slope of beta 1, and if x2 is equal 1, then we will have a slope that is beta 1 plus beta 3. So that means that we are changing not only the intercept through this term, but we are also free to change the slope of the dependence of y onto x1 when x2 takes a different value. So now the interactions are changes in the slope and intercept of the regression line. Okay, so here we have an example where we have a categorical value that takes a categorical variable that takes three values, a, b, c, and then we see that for the values a and b or a and c, the observations are almost in the same line, while for the b observations we have a different slope and different intercept. So this is how the scatter plot looks like. So we readily recognize these different slopes here. Okay, so now we use x2 in the wrong way. So we encode it as a numerical value that takes or numerical variable that takes the values 0, 1, 2, and this x2n means that, so x2 numerical, and then what we see is that the estimate of the x2 numerical is not significant. Still, with the other two variables, we are explaining quite a lot of the variability, so almost 87% of the variability. But then we see that the regression line doesn't really, it goes a little bit in the middle of all the observations, so doesn't really capture these two trends. And when we do the residual analysis, we see a very specific pattern in the plot of the residuals versus the fitted values. So that means that our model has been misspecified. So now we use x2 in the right way, so by expanding it into two dummy variables, and now we will have estimates for x2 when it takes the b value, to x2 when it takes the c value. We know that the value for a is 0, so so it seems that x2b is extremely significant, x2c is not significant. And now the r squared is much better than it was, and still in the residual analysis we see some pattern that we may try to get it better. So now, because we didn't consider the interaction, when x2 takes the b value, what we are doing is shifting down the regression line, so we are just changing the intercept. So now we consider the interaction. So by considering the interaction, now what we see is that now we are changing the slope and the intercept. We don't see any specific pattern in the residual analysis, and here are all the estimates for the different parameters. So we have the intercept, we have the slope of on x1. We don't have the value for a, x2 equal a, because we know that when we have three possible values for a categorical variable, we only construct two dummy variables. So these are the estimates for the two variables. So the one for x2 equals c is not significant, but when x2 is equal b, then it is significant. And the reason is that this other line is only for b. So this line, yellow and blue, is for a and c, and then the one that is different is b. So that is why the intercept of c is not significant. And then we have again the slope of c is not significant, but the change in the slope when we have b, it is significant. And now the amount of variability explained is also pretty high. It is higher. Here it was 94%, here it is on 97%. So this is all for the whole lecture. So with this we finish regression, and see you next time.